Welcome. We now begin Chapter 5, titled Discrete Probability Distributions. So we'll be expanding on the foundations of probability that we've established and now move forward and describe what are called probability distributions. So first, let's start with the definition of a random experiment. So a random experiment is any activity that results in one of several possible outcomes, but the outcome cannot be predicted prior to conducting the experiment. So a nice simple example of a random experiment would be tossing a coin. So I know I could get a head or a tail, but I won't know which one until I actually conduct the experiment. So we're going to move forward though and perform 2 trials of the experiment. So N here represents number of trials. So we're going to toss that fair coin, but we're going to do it twice. And I'm going to complete a tree diagram here to represent that sample space for 2 trials. All right, so first toss of the coin, 2 branches here because it could either land heads or tails. All right, so that's our first toss. And then we are going to toss that coin again. And on our second toss, we could get either a head or a tail. So the possibilities here, you might get a head followed by another head, or you could get a head followed by a tail, or a tail followed by a head, or a tail followed by a tail. And because the coin is fair, each side being equally likely, those 4 outcomes that are possible, 1, 2, 3, 4. So we have 4 outcomes possible. Each of them will be equally likely. All right, so your chances of getting a head followed by a head, 1 out of those 4. All right, so that was probability, but now let's expand on our knowledge here and introduce random variables. So we're going to use X to represent a random variable, and it's simply a rule that assigns a numerical value to each outcome in our sample space. So let me introduce our random variable here. I'm going to let X be the number of heads in 2 tosses of a fair coin. So if you pick up a coin and you toss it and you get a head followed by a head, X, the number of heads you just got, is 2. Or if you got a head followed by a tail, you just got 1 head, or a tail followed by a head, you just got 1 head, or you lastly could get a tail followed by a tail, and that would mean you got 0 heads. All right, so our random variable in this case is called a discrete random variable because it can only take on a countable number of distinct values. So it could either be 0, 1, or 2 heads. So in this chapter, we'll deal with discrete variables. And then in the next chapter, we'll talk about continuous random variables. But for now, we'll focus on discrete. And our next step then, we've defined the random variable. Our next step is to create what is called a probability distribution. So essentially, we're going to look at possible values of X, 0, 1, or 2, but now we're also going to include the probability that each of those values of X occurs. So let me go here first. So X is the random variable. So this is the probability of X being exactly 0 heads. So 0 heads occurred once out of those 4 equally likely outcomes in our sample space. So I'm going to do this in fraction. So X occurred once, X equals 0. 0 occurred once out of those 4 possible outcomes. All right, the probability that X was exactly 1 head, well, that occurred 2 different ways. So 2 out of those 4 possible outcomes. And then 2 heads, just 1 way out of the 4. So now that we have those probabilities, this table will be called a probability distribution. So I'm going to list everything X could be You might get 0 heads, you might get 1 head, or you could get 2 heads. And now we include the probability of each of those values of X. And I'm going to switch to decimal here. So the probability that X is 0, 1/4 would be 0.25. So this notation, the capital X here just represents X in general, and then that lowercase x is each one of our possible values. So probability X was 1. So the probability X was 1 was 2 out of 4, or 0.5. And then the probability X is 2, that was 1 out of the 4, that's also 0.25. All right, so to be a probability distribution, we have to list everything X could be, along with the probability of each of those possible values. So when I add, so there's my capital sigma, when I add those probabilities together, and I'm just going to say P of X, so just to make our notation a little simpler, if I add those probabilities together, then I have to get 1. So if we add those together, we will get 1, or 100% chance. So we know that there's a 100% chance that you're going to get 0 heads, 1 head, or 2 heads. So that is called a probability distribution. And we could also put that information into a graph. So you'll see here my x-axis. I'm going to label that axis over there. X was the number of heads in our 2 tosses. And we might get 0 heads. And now the height of each of these bars represents the probability of that particular value of X. So we might get no heads. That occurs 0.25, 25% of the time. And I'm going to just go back to fractions here. So that happened 1 out of 4 times. 1 head happened 2 out of 4 times. So there's your 0.5. And 2 heads occurred just once, 1 out of 4 times. So again, that is called a probability distribution. And we are probably going to focus more here on presenting them in table format, but the graphs, I will show you more of those as we move along. All right, so let's just get used to notation and go through again the requirement here. So to be a discrete probability distribution, the one requirement we have is that when we add our probabilities together, we have to get 1, because we will always be listing every possible value of X along with its corresponding probability. So let's take a look at an example where they've given us the information already as a probability distribution. All right, so pet registration records show that households in Shippensburg have from 0 to 3 registered pets. We're going to let X represent the number of registered pets in a randomly selected household. And here's the probability distribution of X based on the town's records. All right, so the probability a household has 0 registered pets is 0.15. And I'm going to just speak in percent here. So 15% chance a household has no registered pets. There's a 46% chance they have 1 registered pet, a 23% chance they have 2 registered pets, and then finally a 16% chance they have 3 registered pets. All right, so if I were to add all of those probabilities together in decimal format here, we would get 1. As percents, of course, we would get 100%. So that means we've represented all possible values of X in the town of Shippensburg. All right, then we're going to answer some probability questions and get used to notation here. So find the probability that the selected household has more than 1 pet. So probability, capital P there, probability that. So the new thing in chapter 5 is our random variable X. And we want to know the probability that X is more than one pet. So more than would be greater than, more than one pet. All right, so having more than one pet could mean more than one would start with two pets. So probability X is exactly two pets, or, so there's our addition rule, or more than one would also include people that have 3 registered pets. All right, so probability that X was 2, we'll work in decimal here, 0.23, plus the probability X was 3, 0.16. All right, so we'll add those together, and that is 0.39, so 0.39, or I'll just speak it as a percent as well. There's a 39% chance that a randomly selected household would have more than one pet. All right, let's try B. So find the probability that the selected household has at least one pet. So just a reminder, at least one would be one or more, or said another way, no less than one. So at least one. All right, let's write that question in symbols. Probability that X, so at least one, so one or more would be greater than or equal to one. So that would include the probability of having exactly one pet or two pets or three pets. All right, so again, just getting used to notation here and the inclusion of our random variable and learning how to change those English phrases into our mathematical symbols. And then we can go through that table and substitute. So one pet, that was a probability of 0.46. Two pets was 0.23. Three pets, 0.16. And before I add those up, I'm just going to come up here and box that in so we know that all of those probabilities together add up to 1. And we're now looking for those 3 probabilities. So if we add those, 0.46 plus 0.23 plus 0.16, that is 0.85. All right, I'll go ahead and write that as a percent as well, 85%. All right, so rather than using that method, it's going to be important in chapter 5 that we return to this idea of the rule of complements. So another way to find this probability by applying the rule of complements. So I'm going to come back here. So 2 events are complements if together they make up the entire sample space. So the only probability not part of the probability that we're seeking. So this probability was X greater than or equal to 1. The only other possibility would be that X equals 0, no pets. So the complement of at least one pet, the only other possibility would be no pets. So I know that when I add the probability of an event plus the probability of its complement, I have to get 1. So this allows me to find the probability of X greater than or equal to 1 using the rule of complements. So if I want to know my purple value here, I can do 1 minus my red value there. So I can do 1 minus the probability that X equals 0. All right, so just another way to get to the answer. So we could have done 1 minus the 0.15 And that would have gotten us to the 0.85 as well, or again, 85%. All right. So our next goal will be to look at examples where we have to create the probability distribution ourselves.